after the coffee break. I hope you had a good coffee or tea. And we're very happy to have two great speakers in the second part of this morning session. And the first of those is Hans-Henning Klaus. Hans was going to be in person at Davis, but like all of us, in fact, he had to cancel just a bit before everyone else did. And he's going to tell us about his work on superconductors with time reversal symmetry breaking, strontium ruthenate, and potassium doped barium iron 2 arsenic 2. We're really looking forward to it. Thank you, Hans. And I guess it's 45 minutes, but if you can allow about 15 minutes for questions, that'd be great.
Yeah, sure. Thank you very much, Piers, for the introduction, and thank you for inviting me to present our results here. Yes, unfortunately, I could not come. I was more or less going already last week, and only then I realized how the Omicron version started also in the US, unfortunately. Okay, yes, I want to talk about time reversal symmetry breaking and superconductivity in strontium ruthenate at the potassium doped barium 122. And come to the next slide somehow. Doesn't work. That is the only thing I didn't test. Why doesn't it work? Weiter. Okay, I see. Hopefully that gets better. Okay, so first I want to say some words about the models for basically, in my talk, only two-component orbital time reversal symmetry breaking superconductivity. So yesterday we had already a talk by Valentin Taufour about a very new, different kind of time reversal symmetry breaking superconductivity. These are more or less a little bit more conventional time reversal symmetry breaking superconductors I want to talk about. And mainly, the purpose is that I want to differentiate experimental between chiral and non-chiral two-component time reversal symmetry breaking order. Good. After this introduction, I will then come immediately to the results on the well-known, one of the first time reversal symmetry breaking superconductors at all, strontium ruthenate, and discuss our recent work in uniaxial and hydrostatic pressure work. And then in the second part, indeed, I will show also muSR data, but also a lot of thermodynamics and transport data on the barium potassium 122. Here we clearly see a non-chiral superconductivity in a certain fraction of the phase diagram, which was predicted, and we have observed that in recent years. But moreover, then we found also that there are really that fluctuation-induced time reversal symmetry breaking states above the superconducting state in the normal metal. And this is probably the newest and most exciting stuff. Okay, the first work, all on the work on the strontium ruthenate, was mainly done by Vadim Grinenko and Srinanda Ghosh. Srinanda is the PhD student who worked on that, and Vadim, the postdoc for many years, worked in our group for 6-7 years, worked in our group. Of course, a lot of work has been done with muSR, mostly at PSI in Switzerland. Rustem Kazanov was very important in this case. We developed actually a specific dedicated uniaxial pressure cell for muSR, which can also be used for neutron scattering. And that was done in cooperation with Clifford Hicks, and he is mainly responsible for also the engineering part of that. The samples for strontium ruthenate came mostly from Yoshi Maeno and Naoki Kikugawa, and a lot of theory support for the interpretation came from the group of Manfred Siegelst. Okay, so short introduction. So a small fraction of unconventional superconductors break time reversal symmetry breaking, and some of them, most of them, due to an imaginary two-component order parameter. So we have two different order parameters, delta 1 and delta 2, and in this complex combination, coherent complex combination, they cause orbital currents. And basically, this appears as a result of frustration in the pairing interaction. And then you can see what kind of order parameters are forming this coherent state. And either these two states are degenerate by symmetry. So for example, in the famous PX and PY proposition, which was initially suggested for strontium ruthenite. These have basically come from the same irreducible representation. So in principle, they should have the same energy. Therefore, they are degenerate order parameter by symmetry in the tetragonal lattice. In other cases, you can have two non-degenerate composite order parameters. So basically, when these two order parameters come from different reducible representations, then they can have different absolute values, but they can also have other angles in between the two components. They should not necessarily be 0 and pi. And other examples are here S plus ID or D plus IG or so on. And yeah, and this is in the first place, we wanted to differentiate between these two cases for strontium ruthenate. And then in principle, one idea is really to apply a uniaxial strain along the A or B direction in this tetragonal lattice, and thereby basically lifting this degeneracy between the two order parameters. And then what one should expect to see is actually that whereas at 0 uniaxial strain in strontium ruthenate, we could very well show again that these at the same point when the sample gets superconducting, it also gets time reverse symmetry breaking. But for that, you need the two components. So if you break the symmetry, one of the components will be stabilized and the other component will be destabilized. And that means you will first see some superconducting phase, and that at a lower temperature, the time reverse symmetry breaking superconductivity. On the other hand, if we look in the non-chiral states here, basically there is no reason that, for example, the maximum of the time reverse symmetry breaking phase reaches up to TC. If you want to have that coexisting here, you actually need some fine tuning, because from the very beginning, they have different order parameters and energies. But then, of course, also, yeah, these are basically a competition. You can think of this as a competition between one state which is stable at a certain parameter range and another state which is stable at another parameter range. And in this case, what is important, if they are degenerate at this point, basically many more perturbations will be able to separate these two combinations. Whereas here, you really need to break the symmetry between the two components. All right, and in particular for the tetragonal systems, and in particular for strontium ruthenate, these things has been discussed. So now, since we knew since 2 years that basically this is not a triplet superconducting state, the only chiral solution which is there is basically this dxz plus minus idyz state. And if we assume that in certain kinds of models, then indeed TC and T time reversal symmetry breaking temperature must split under symmetry breaking uniaxial pressure. And if we apply, for example, hydrostatic pressure, which will not lift the degeneracy between X and Y directions, then they should not split. And if I look at the accidental degeneracy states, which come from different irreducible representations, in principle, they should split under uniaxial pressure, but also split under symmetry conserving hydrostatic pressure and, for example, disorder. This, of course, is the last one maybe is a hand-waving statement, because in some of these models here, you can fine-tune the parameters actually that eventually they do not split under hydrostatic pressure or disorder. Nevertheless, this was the proposition for our work in the beginning. So why do we do that? Why is a muon spin relaxation a good way to test it? Certainly with muons, we can measure the superconducting transition. And this is one out of 2 methods to detect the very weak internal magnetic fields in the time reversal symmetry breaking state. We have seen that already yesterday. And for strontium ruthenate, this famous sample, of course, the first work was done by Graham Luke back 24 years ago already. And he could show that really right at TC, the muon spin relaxation rate starts to increase. So, and then he also measured even earlier uranium platinum 3. And there you could also see that below this compound, the second transition here, there's also an upturn in the zero field relaxation rates. And this comes actually from spontaneously appearing very weak fields. So this rate of increase really these are small numbers in the units we use, 5,000s or 500s of an inverse microsecond. That already tells you this is at the lower resolution we have really in this μSR. So one really has to work hard to see that. So this is another sample here on the right side, strontium and platinum arsenide. This we did some years ago. And also there you see that below TC, there is an upturn of this relaxation rate, and it's really very small. So the fields which you need to see this kind of increase are of the order of 1/10 to 1 Gauss. This time reversal symmetry breaking is found in a handful more systems. Then lanthanum, nickel, and gallium, we have heard the newest results yesterday. Praseodymium osmate is known for a long time, and also the non-centrosymmetric superconductors here and some others. Okay, particular for strontium rutheniate now, again, the experiments we wanted to do. So in the beginning, to resolve this question of what is a superconducting order parameter and strontium rutheniate, an open question for basically maybe 10 years, 15 years at least. And of course, if you want to separate it, it's a good idea to modify your system and change symmetries and so on. And this idea, as I said, came basically from Clifford Hicks and Andy Mackenzie from that group. And when I saw this sketch of the theoretical expectation, it was clear that muons would be a nice thing to do, because to see the second transition here inside the superconductor, the upturn of time reversal symmetry breaking, you can only do with μSR or with polar Kerr effect. Just for time reasons, I will not talk about polar Kerr effect today. Okay, and so in the beginning, they certainly did this experiment with thermodynamics, so magnetic susceptibility, and then they could certainly test that again, if here is a zero pressure state, if you apply compressive strain, that you have an upturn of TC. Actually, it's more than doubles here. And then at a very high strain, it comes down again. And this is basically due to a Van Hove singularity, which is at least close to this maximum. However, in these experiments, they could not detect the second phase transition. So here's a picture now, new data, really to see this Van Hove singularity at this Lifshitz transition here. Basically, if you apply something like 0.5% of uniaxial strain, basically like in the AB plane spherical Fermi surface touches the Zoom boundary, and then it turns and it forms a longer open circuit here. And this is basically the Van Hove singularity at the Lifshitz transition, and which is responsible for this effect. Also, one can see they measured that the HC2 as a function of at the Lifshitz transition is really strongly increased, whereas an unstrained strontium rutheniate with a field along the C direction is much weaker. So, okay, we designed this cell which we had to use for muons. Muons had to use much larger samples because typically we have here our sample on which a muon bin comes in, let's say from the right side, which has a diameter of 7 millimeters, and the muons have a penetration of a few hundred micrometers. So clearly we need actually quite a strong force if we want to now pull or push on that sample in one single crystalline sample in one direction. So actually it's also a piezoelectric driven cell. It can apply forces up to 1000 Newton here on the sample at low temperatures in the dilution fridge or in the helium-3 cryostat. And meanwhile, we have also used it for different kinds of experiments. It's particularly designed for a facility experiment where you have basically the force generator detachable from the sample or vice versa. So you can measure different samples one after the other in a beam time. So, and here are the results. Basically, here is, I will plot it in the way you will see, where's my pointer here? On the left here in the middle, you see the μSR spectra. So above TC is the green line. You see some weak relaxation as a function of time. And then if you go in the superconducting state or below the time reversal symmetry breaking phase, to be more exact, you see a stronger relaxation. And here on the right side, then you see this relaxation rate, for example, here at 0 strain, the green points. And together we plot actually the AC susceptibility signal, which we measured in situ in the same apparatus with a little AC susceptibility measurement just behind coil system, just behind the sample. And just it's a little bit weird that we plot the diamagnetic transition is here just for a nice comparison is when it goes up, when the system goes up here. So the black line for the susceptibility. Okay, and now you see it here at 0 strain, then at 0.28 gigapascal, and then at minus 0.43 gigapascal. And what you can clearly see is that on one hand, the superconducting transition goes up, with the black line here, and that actually the time reversal symmetry always appears at nearly the same temperature. I can hardly move my pointer here. So it basically, all these appearance temperatures are on the red line. And that means we are going up so far here, these 3 points I showed here. So now we go much higher in uniaxial strain above the Van Hove singularity here in this region here on the left side. And you clearly see that now we have really in the susceptibility superconducting transition at high temperature, 3.4 Kelvin. And still there is time reversal symmetry breaking. Here are the points. Here you clearly see that there's an increase of the relaxation. And this holds up actually to the maximum pressure of 0.82 gigapascal. So it clearly tells us that time reversal symmetry breaking state exists above the Van Hove singularity. However, if you go to even higher strain, so here this is about there's a value 1.0 gigapascal, then suddenly the electronic state changes, and actually you see here on a very fast relaxation of the muon signal below 7 Kelvin and oscillations, which is a clear indication of magnetic order. And so if you look closer, you can deduce the internal field as a function of temperature. You see a nice magnetic order parameter function. And one can also say that it coexists at least with superconductivity in some part of the sample below 3 Kelvin, let's say. And one can see even some sort of interplay between the superconductivity and the magnetism, because if I look at the lower view graph and the relaxation rate here, that when superconductivity sets in, let's say about 3 Kelvin, there is like an additional increase in the muon relaxation. So this magnetic order really has nothing to do with the time reversal symmetry breaking, because the internal field here is a factor 50 times stronger than what is usually seen in the time reversal symmetry breaking state. So, there were already predictions that one can see, of course, Fermi surface nesting, in particular, close to the Van Hove singularity. And basically, this is probably the case which we observe, and we have not seen the proposed spin density wave order below the Van Hove singularity. Yeah, and this is basically the phase diagram which turned out from these studies. So here you clearly see the splitting of the superconducting transition temperature and time reversal symmetry breaking transition temperature. Okay, and now it turns out that still this is not a clear separation, because, as I said, if you have at 0 strain accidental degeneracy, it could well be described by non-chiral order. So then in the last years, we also did other experiments. For example, we did some small lanthanum doping, from which it is known that it suppresses strongly the TC. For example, in this doping from 1.4 Kelvin to about 0.8 Kelvin. So we reduced TC by a factor of 2. And indeed, in this experiment, also, as you can see, the time reversal symmetry breaking temperature is reduced. So here, again, the red points show the onset of time reversal symmetry breaking, yeah, in terms of the data quality at the same point where TC is. So clearly, this is already favors a chiral superconductivity, because both points move together, but it's not a proof. So, and the last experiment on strontium ruthenate we did was actually applying hydrostatic pressure. This also preserves the symmetry in the AB plane. And it's also known that if I apply hydrostatic pressure, I suppress TC from 1.5 Kelvin to, let's say, about 800 millikelvin in pressures up to 2 gigapascal. This is what we could do with muons. And here I just show some data. And here, so basically, we measured even with muons at 0 gigapascal pressure and at some pressure of 1 gigapascal. We measured the superconductivity by measuring in transverse field, basically the flux line lattice. And you can see if you apply some pressure, yes, you suppress TC and the flux line lattice occurs at a lower temperature. And here now there are the zero field results for the same pressures. And as you can see at room ambient conditions still, yes, we have the same temperature, TC coincides with time reversal symmetry breaking temperature, but the same holds again for the pressure here. We did that for some more pressures. And then we look at this diagram here, you now see the time reversal symmetry breaking transition temperatures on the vertical scale and on horizontal scale, the superconducting transition temperatures, and all these new data. So the normal ambient condition sample is here. Now you apply hydrostatic pressure or you dope the system, and all these points lie exactly on this line where these both temperatures agree. And here I plotted just the 2 points out of the uniaxial pressure experiment, which clearly show this deviation from that line. So taking into account all these results, we think that a chiral 2-component order parameter is most probable for strontium ruthenate, and it is a kind of difficult from theory grounds because actually there's a nodal line in the z direction at the plane in the AB plane, and therefore it in principle requires interlayer pairing. But however, there are some new models which do not do the coupling superconducting interaction in Fourier space, in K space, but in real space, in some local models of the orbitals. And then there's some more flexibility, and this studies can actually are consistent with this dxz plus minus I dyz as a realistic model. Yeah, so this was actually the first part, and now I want to come to the second part here, and which is a BKFA. And yeah, this different group, many more and other people were involved. Again, Vadim Grinenko was a very important player. Actually, when he came as a postdoc into my group, he suggested this project to look for the time reversal symmetry breaking, and he has done most of the work in planning and also doing many of these experiments by himself. Of course, other people are also important. The samples, in this case, you have to have very high homogeneity and very nicely determined potassium content, which is not so easy in that system. And these samples came from the group of Shulho Lee from Japan. We did a lot of thermodynamic measurements, specific heat, and also ultrasound, microcalorimetry, and thermoelectrical transport are very important, as we will see. So we did Nernst effect and Seebeck effect measurements also. And here the theory support was very important to understand this time reversal symmetry breaking effect above the superconducting state, and for that Igor Babayev is responsible, his co-workers. So barium 122 doped by potassium has the advantage that you can really dope throughout a very large doping range. Most people discuss usually the interaction between magnetism and superconductivity here at low doping, but we are again interested to see competing superconducting states. And these superconducting states appear here close to a Lifshitz transition, which occurs in that system at high hole doping. So This was already noticed in work more or less than 10 years ago. So basically, if you whole dope a lot with more than 0.4 up to 0.1, basically the electron band at the M point, which is usually below the Fermi surface, here's the electron pocket, that will be moved up. And basically, you have a Lifshitz transition where the electron band is above the Fermi transition, Fermi level. And then you lose a whole Fermi surface. And then, of course, you basically need, you may have two different sorts of superconducting order. Let's look at that. So if we are at low doping, we have basically typical S plus minus order. So here we have our whole Fermi surface in the center and our electron Fermi surface at the not M point, X point in this representation. And this is the one which will appear. But as long as I have the three Fermi surfaces, I can have superconducting order on all of these Fermi surfaces, usually with either 0 phase difference or with 180 degrees phase difference. And this S++1 model basically is one of the possibilities at low doping. So at the high doping, we've lost the electron band, and then you can make S plus minus superconductivity only between the two bands, which are left over here, so to speak. And that means somewhere in between, you have this Lifshitz transition where this electron band is lost, and then you can have something which is called incipient band superconductivity. When the electron band has just moved away from the Fermi surface, but still the difference from Fermi level is smaller than the possible gap energy, then it can still contribute a little bit, and it can carry some Cooper pair on the Fermi surface. And then basically, on the same time, one of these Fermi surfaces has to turn its order parameter from up to down, and you can have then this situation where you have angles, different phases between the superconducting order parameters, which are not 0 or 180 degrees, and this gives rise to S plus IS, time reversal symmetry breaking superconductivity. And indeed, we have found it in these single crystals, these nice new single crystals. So here is a doping of 0.68. Again, muon spin relaxation rate in 0 field, nothing to be seen, no change, just at TCs, which are of the order of 10 to 20 Kelvin here. Then at 0.8, we can see that there's a slight upturn of the relaxation rate. And at much higher doping, again, 0.85, a little bit higher doping, it's again completely flat and no time reversal symmetry. So if you do a lot of samples and also combine it with thermodynamics, in particular specific heat, you can be found that there's really this kind of dome of time reversal symmetry breaking states inside these superconducting phase at high doping, but it's a bit above the typically found position of the Lifshitz transition. Whereas one has to say the Lifshitz transition appears at different dopings for different situations in the C direction, because there's warping of the Fermi surface in C axis. So this is certainly broadened, and this one can see here, for example, in the normal state Summerfield coefficients. There is no real peak here, like what you would expect at a Lifshitz transition. It simply starts to increase here. Okay, so nevertheless, this was the first result that we really found this proposed state in a position where you have this competition between the nodal S plus minus on one side and this so-called nodeless S plus minus on the other side. Okay, if you look a little bit closer, you may think, well, what is this point here? So it looks like really that we found time reversal symmetry breaking eventually above the superconducting transition. How can that be? Well, are there fluctuations in the system, increasing superconducting fluctuations, for example? And latestly, we did actually spontaneous Nernst experiments and on normal Nernst experiments at certain points in the phase diagram. And basically, you find fluctuations above TC. And if you look at this line here, basically exactly there where we find our phase, actually TC dropped. We didn't care too much before on this point, but now seeing that actually superconducting fluctuations are up to higher temperatures, it becomes interesting. Why does it go down here? And are these indications for strong fluctuation effects? And this is at least the first indication. So now let's again look at the data, And indeed, in the old data, we found that in one of these samples, 0.8 doping, there is actually some increase of the relaxation rate above TC, if one looks closely. But in the first publication, we thought, well, just one data point, it's not even clear, if you look at the scattering of the data, that this is really new physics. So in between, we have done these Nernst measurements. And if you look here, exactly you see that there is a spontaneous Nernst signal exactly above the appearing above TC. This is again susceptibility data here, and it appears right there where we have here the onset of time reversal symmetry breaking. So at least this is an indication, or even some evidence, that we have time reversal symmetry breaking transition above TC. So then we started to do a lot of thermodynamic and transport, which was luckily easy to do due to the situation in Dresden that we have many groups working in correlated electron physics doing thermodynamic and transport. So now I will walk you a few minutes very shortly to first the situation in one of these systems, which is very prominent for that, 0.8 doping, 0.79, and look at the zero field data. And now here again, we have the susceptibility data, so which defines TC here, about 11.5.
We're up to half an hour. We're up to 32 minutes, just let you know.
Yes. Thanks.
Okay,
and then you see that already in specific heat, you see an upturn at a higher temperature. Then if we look at transport, electrical resistivity or Seebeck coefficient, it also see that they are already starting to fall down above TC. So there are kind of superconducting fluctuations seen from that. And here again is a spontaneous Nernst effect, which clearly appears here above TC. Then we also measured the field dependence of these effects. And at all fields, 1 Tesla, 6 Tesla, and 9 Tesla, you start to see even a kink in the specific heat at a second transition above TC, which is actually defined by the onset of the spontaneous Nernst. And this happens at all fields. Just one last comparison with other samples here. This again, 0.77 is the sample which shows this effect. Here again, spontaneous Nernst, now together with resistivity, but here resistivity on a logarithmic scale. So you can see clearly spontaneous Nernst at different fields appearing here. And more or less on the low side of that, you see the downturn of the resistivity. And this is not there at other dopings. Some fluctuations at lower dopings, but clearly not there at higher dopings. And we'll not discuss the other results. If we put together this into a phase diagram for one material, now temperature and magnetic field, we identify a clear appearance of stability of this new phase, which we call quartic metal, between the superconducting state and this second transition, which we call TZ2. I'll come to that name in a minute. And we see a clear, relatively large temperature range of fluctuations in the Nernst measurement, Nernst and spontaneous Nernst measurement, which indicates that really strong fluctuations are at all magnetic fields present in these samples close to that doping. Yeah, and the interpretation, why do we call it quartic metal? Basically, the model is that whereas in the superconductor, of course, we have the phase coherence, spatial phase coherence between the 3 different ordering vectors on the different Fermi surfaces. And in the quartic metal, we lost the superconducting coherence, which means we lost the phase coherence. But still, there is basically, you can differentiate between left chiral and the right chirality of this order of these three local components. And this is the order parameter. The order parameter is that you can either have the same chirality in these 3 orders here or a different one, and the opposite one, 2 chiralities. And the normal state here is basically where it's completely disordered. Yeah, the conclusions are on this side. we have found some new phase above the superconducting state, which is characterized by the symmetry breaking in this model. We identified it from spontaneous Nernst effect, increased muon spin relaxation. And we also see signatures in thermodynamics in specific heat and ultrasound, which I didn't show. And it's clearly not a superconducting phase because there's no Meissner effect and still a finite resistance. And yeah, with this, I want to come to the final conclusion. And yeah, with these muons, we can look nicely at this very weak field in time reversal symmetry breaking superconductors, and we use it for the purpose of breaking the symmetry of that system in uniaxial strains, or just modifying the state by hydrostatic pressure or by impurity doping in strontium ruthenate to basically come to the conclusion that there is a chiral time reversal symmetry breaking superconducting order in strontium ruthenate. And in the barium potassium 1-2, first of all, we could prove that there is that the theoretical proposal that there might be time reversal symmetry breaking superconductivity in the non-chiral form is really true. But we have this unexpected observation that there is additional phase in the normal metal. And from the theory model of Igor Babaev, one can call it a quartic metal because it's basically a correlated state between 4 fermions. Yeah, thank you very much for your attention.
Okay, thanks for a great talk, Hans. And now we're open to questions. Questions from the group, please. Okay, Valentin.
Can you hear me okay? Yeah.
Yes.
Thank you very much for a very nice talk. I had a question on the dome of time reversal symmetry breaking phase. On the left, it is bounded by the Lifshitz transition. But then do you have a sense of why it disappears on the right side? Like what is
in principle, it occurs. I mean, the left Lifshitz transition is a prerequisite. Yeah, so which destabilizes the nodeless S plus minus order here on that side, and then you have the competing state, which is basically there the nodal S when you have got rid of the Fermi surface, and then it's on the right side because we have this incipient band figure that as long as this electron Fermi surface is still close to the Fermi level, it can contribute to superconductivity. And I think this pushes this kind of the Green's phase here a little bit to the right.
Okay, and if I can ask a follow-up, do you think it is related to this, if you take the pure potassium 1-2, under pressure, it has this kind of V-shaped TC that was discovered. So is that possible that this is the same phase?
Yeah, in principle that depends on. I'm not 100% sure what happens with the electronic structure, with the Fermi surfaces under pressure. So I'm actually not now available. I don't have it in my mind. If you also find something like a Lifshitz transition, then you might get to see similar physics occurring.
Mm-hmm. Thank you.
Elio, nice to see you. You're up next.
Nice to see you. Thank you for the beautiful talk. I have a quick question just about the experimental measures that you use for seeing this time reversal symmetry broken metallic phase above this S plus IS state. If I saw right, you didn't measure usual electrical Hall resistivity, which I would have thought maybe is the most natural thing to measure. So how come? Or
I think there is, well, we were looking for methods which see the time, which are a little bit prone in the first place for the time reversal symmetry breaking, for fluctuating time reversal symmetry breaking. And for that, well, thinking back on, for example, fluctuations in the cuprate, the pseudo-gap phase, where, for example, they see strong Nernst signals. That's why we came to do all these the thermal transport experiments. So there is no specific reason why we didn't try Hall measurements. And then the another thing we looked for symmetry, to see the symmetry breaking, and that I haven't shown, but we see also effects in ultrasound. So really to see this aspect of symmetry breaking, we did that.
Great, Nick.
Hi, Henning. Really nice talk. So I was curious, is there any significance to in the strontium ruthenate? I mean, the time reversal symmetry breaking temperature is more or less independent of stress, whereas the main temperature goes up. Is there any significance to that? I mean, does that say something about something fundamental about the material?
Yeah, this is actually it is a surprise. So in particular, it is basically temperature independent. If you start with weak uniaxial stress, then if you go beyond the Van Hove singularity, then it goes down and it somehow disappears. There unfortunately, these are long-time experiments, and we could not look closer at this region, for example, here. But yeah, it is consistent. The fact that it goes down so weakly, or even not at all, is consistent with the fact that the specific heat at this transition is very weak. So in principle, if you think there are two order parameter components, one coming up at a higher temperature, one at a lower temperature, one can think on the fact that they both give specific heat. Yeah, and if that would be true, and you looked into the in the Landau model and calculated, then you would have a stronger gradient in the suppression of the time reversal symmetry breaking. But actually, so far, any thermodynamic signal in specific heat is less than 5% than what you have at TC here. So that actually, and at the end, that at least hand waving arguments, it might explain why this is more or less flat here. You basically lose most of the entropy in the superconducting transition. Which is fine, which is perfectly fine if you have a strong splitting. So if you have any kind of model where you have two following up order parameters, then the bigger the distance is in temperature, of course, the more entropy will be absorbed by the higher transition at all. But clearly in this range at low uniaxial strain, the physics is not fully clear at the present moment, I would say.
It's remarkable, actually. Yeah, good point, Nick. Valentin.
Well, just following up on this, so you presumably there is no twinning effect at those stress, right? You're above the T-twinning.
Yeah, basically these. Well, we are basically these. We apply the uniaxial strain really on a single crystal in one direction, and we get like this is here we are at like 1 to 2% strain. So it's basically just one orientation you always look in this uniaxial in the experiments at this uniaxial strain.
Mm-hmm.
So it's completely detwinned, if you wish.
Okay. Yeah.
I guess one could rephrase the question: what does the constancy of the time reversal symmetry breaking transition say about the Ginzburg-Landau theory, the underlying Landau-Ginzburg theory? Does it place a constraint, and is there important physics there?
Yeah, we are not 100% sure. Well, first of all, what one has to do and what we are doing now is measuring the other directions. So for example, this was a 100 direction, yes, along A axis. Now we have done experiments along 110 in the diagonal, where you should, for example, change the energy stability of both phases the same way, both order parameter components. And that direction has one advantage, I should say, and that is we don't have this Van Hove singularity, which has a huge influence on that physics here. Yeah. So the Van Hove singularity, I mean, the density of states at the Fermi level effect is kind of overwhelming in this orientation. Yeah. So maybe that one has to disentangle this effect from the subtle effect of the stability of the order parameters, and I don't know how to do that in the Ginzburg-Landau model. Really, I'm not sure if one can do that.
Kanka. Thank you.
Yeah, I had a question. This may not be so feasible. So in the strontium ruthenate, you did this experiment under pressure, right? So the barium case, instead of doping, could it be done under pressure as well? Except the pressures are probably prohibitively large.
Yes.
Because there are theoretical calculations which show there's a Lifshitz transition under pressure as well.
Right. Okay. Yes, I think this can be done. There are some experimental issues. For example, in the high pressure cell, you need quite a lot of material in USR, for example. Here, to really have good crystals of the barium potassium, we measured like 100 crystals, which were small, and really pick out those which have the same superconducting TC, but to pick out those which have the same lattice constants, and then form like a sample out of 4 or 5 of these little platelets from USR. And for high pressure, you need even 10 times or 20 times more of these samples. So it's a sample issue that is, in the first place, it's difficult to do hydrostatic pressure.
Also, would it be a problem because this Lifshitz transition, at least the paper we wrote, we say that this Lifshitz transition is tied to this tetragonal to collapse tetragonal phase.
Right.
So being in the collapse tetragonal phase is going to cause another issue then?
Yeah, not necessarily for the muon experiment. In principle, the muon side may change, but regarding superconductivity and time reversal symmetry breaking, the real position of the muon is not important.
Okay.
Last question then, Luca de Medici.
Hello, very nice data. Sorry to bring you back to barium potassium compound. I was just curious to understand if you have related the behavior you find with this peculiar behavior of the Summerfield coefficient. Did you mention that? So what is the relationship?
First off, well, we don't have I don't have a strong opinion on that. Basically, we have some colleagues have made some theoretical calculation of the Summerfield coefficient, but it's in a planar situation, in a planar model. Then you see, for example, a peak. You expect really a peak of the Summerfield coefficient at a Lifshitz transition. First of all, in the experiment that is broadened, but secondly, I said since there's a warping along the z-axis, probably even if you have a nice high quality sample, it's simply washed out. It gets broadened. So, and then so why now we end up, if you go far beyond the Lifshitz transition here on the right side, why we end up with a Summerfield coefficient which is larger here than here, I also don't know.
Well, that is probably a correlation effect. That's what we estimated. But this sigmoidal shape in the middle for me is not so clear, and indeed one would expect a different behavior. So I was just considering if this was a hint towards some explanation related to the behavior you find. Okay,
so I'm not 100% sure, but in this paper, in this Nature Physics from 2020, there is this modeling where that actually I think I don't have a slide here. Which in this 2D model gives the peak here at the Lifshitz transition, and then it also shows some rising gamma value at higher values. But I forgot what the reason was.
Okay.
It's discussed in that paper by the theory.
Thank you.
Okay, well, let's thank Hans for just a great talk, wonderful data, very provocative, and let's go to the next talk.
Thank you.